It's interesting that Maple can give analytic solutions for some boundary value problems for partial differential equations, but not for ordinary differential equations. Now back in 2007, that's some 10 years ago, in a Tips and Techniques article I wrote for the Maple Reporter, I examined how Maple might be used to obtain an analytic solution of a Sturm-Liouville boundary value problem for an ordinary differential equation. Now that's an eigenvalue problem for the ordinary differential equation. So now this is an update on that article, the difference being that here nearly all of the calculations can be done in a syntax-free way. We're going to begin with some notational enhancements, which I will impose through the typesetting rules assistance. View, menu, typesetting rules. Okay? Panel comes up and you make the following changes. In this box where it says add function, we give the name x of x and hit the button add function, and then type in t of t, hit the button here and add function, and check these boxes so that the independent variables x and little t are not displayed, and primes represent differentiation with respect to x, and differentiation with respect to t is denoted by an overdot. Now equivalently, if you're using commands, you would have to type these two commands. The suppress option suppresses the display of the independent variable, and the prime and overdot for differentiation is set with this command. To show you what I mean about Maple's ability to solve some boundary value problems for partial differential equations analytically, consider this wave equation, simple wave equation, utt, uxx, pin down the endpoints of a finite string, for example, give it an initial distribution of displacements, no velocity initially. Maple can produce this solution. You'll notice these are the Fourier coefficients, and it has computed the eigen functions that allow an infinite series expansion for the solution u. And if you would like to see what the commands for getting that look like, these are the commands. There's a dsolve command, a little bit of substitution for the symbol Maple uses for integers, and we have this solution. Now, the way this would be obtained with a pencil and paper would be to assume a separated solution as a product, x of x, t of t, and then you would end up having to solve this Sturm-Liouville boundary value problem. Okay, it's for the x equation, and let's see how one would get that. So here's the partial differential equation, typed it in, I used the partial differentiation templates. Here, let me just give you a quick hint of where you would find it in the calculus palette. There are templates for partial derivatives in here. Here's the second partial. Okay, so I'm going to keep this thing hidden. Separated solution, give it the name u. Evaluate the partial differential equation with that separated solution, and you get x t double dot x double prime t. And the typical thing to do here is to divide by u and also divide by c squared to put the c squared over with t. you're going to get this result, t double dot over t, x double prime over x. This is a function of t, this is a function of x. In order for these things to be equal, they both need to be equal to the same constant. Okay, so here is the way you handle the t equation. You take the left hand side to get the t double dot over c squared t, set that equal to a constant, Bernoulli separation constant, call it lambda, multiply through by c squared t. This is the equation you end up with. Bring everything to the left. Now I'm not going to be looking at this equation. I'm going to be doing the same thing on the right to get the equation in x. Take the right hand side, set it equal to the Bernoulli separation constant lambda, multiply through by x to clear the denominator. X double prime equals lambda x. Move everything to the left hand side. That is the equation we want to solve. Remember, you're going to have to separate the initial order boundary data, x at 0 and x at pi will therefore be 0. And this then leads to the complete Sturm-Liouville eigenvalue problem, which is what I want to be examining in this webinar. Okay, so if you were to take this Sturm-Liouville problem, x double prime minus lambda x equals 0, x at 0 and x at pi equals 0, and hit it with dsolve, which I applied through the context menu, Maple would return the 0 solution. So it does not have the ability to solve the Sturm-Liouville problem. So you have to apply your own ingenuity to get Maple to get past this point. And that's what I'm demonstrating here in today's webinar. So we have homogeneous Dirichlet conditions, and I also will show you what happens if you use Neumann conditions. Okay, so here is the differential equation. You want to solve this, so you make the exponential guess, and you get this characteristic equation as soon as you divide out the e to the mt. When you ask Maple for solutions for m, you get plus or minus root lambda. Now that tells you that lambda equals 0 is a double root. That case has to be solved separately because there is no continuous transformation from the general solution to this special case. So here I'm going to set lambda equals 0. I've got the equation x double prime equals 0, which we recognize has a solution which is linear. And you could, right here, you could say this is a straight line and it can't be 0 in two places. Therefore, both constants have to be 0. If you want to work that out in detail, take this expression, and I'm going to make a function out of it to make substituting 0 and pi in for x a little easier. So this is done with the context menu, assign function s. You get these two equations. You tell Maple to solve them. They're homogeneous equations. Both constants have to be 0. That tells you that lambda equals 0. That case is not an eigenvalue. So here I've cleared S because I want to use it again. And again, that's a context menu thing, pop-up menu. Here's the differential equation. It has equation label 10. We'll want to remember that because it goes back to here. This is where it picked up equation label 10, right there. Okay, so that equation, label 10. And that's what I'm using over here. Okay? So here's the equation. And using the context menu, I have Maple solve the DE. So this is the general solution for the general value of lambda. This does not include lambda equals 0. I'm going to grab this right hand side and I'm going to make that a function, again using the context menu, so that I can apply the two conditions, the boundary conditions here. S at 0 and S at pi are both 0. This gives me two equations. They're homogeneous. Using the context menu, we put these equations into matrix vector form. The right hand sides are 0. The unknowns are C1 and C2, underscore C1 and C2. Grab this matrix, and in order for there to be non-trivial solutions, the determinant of this matrix has to be 0. So get the determinant, set it equal to 0, which is what Maple solve command does. And Maple comes back with lambda is the negative of the square of an integer. This underscore z2 in Maplese means an integer. So I'm going to use minus n squared because it just looks better. So here is the general solution with lambda set equal to minus n squared. Then I start simplifying. So I simplify assuming that n is positive. I get this, but Maple at this point does not know that n is an integer. So I put it into a plus bi form, and this exponential, imaginary exponential, and this imaginary exponential gives me a sine and a cosine each. And then I collect terms. Here's the cosine, and here is the sine, but Maple didn't do any factoring here, but it did some factoring here. Okay? Now, we need to make sure that the information about the boundary conditions is inherited by this expression. So here it has equation labeled 20, and I will set x equal to 0. That has to give me 0. Notice that I get c1 plus c2 equal to 0. And I go back and I want to apply the other condition, x equals pi, but I also want to include this data, which is 21. Set that equal to 0, and Maple comes back with this expression, which if I simplify, I have a multiple. It's a strange looking multiple, but it's a constant multiple of sine n pi. And so I've discovered the eigenfunctions. Now, if we allow ourselves to make use of the dsolve command and apply the boundary data, x of 0 and x of pi of 0, to x double prime plus n squared x equals 0, but put on the assumption that n is a positive integer, you immediately get back that x is a multiple of sine nx. It is unfortunate that one cannot apply assuming through the context menu. That's why we did the calculations that we did here. If the conditions were homogeneous Neumann conditions, the flow through would be the same. You would have the equations s prime of 0 equals 0 and s prime of pi equals 0. It'd give you these two equations. Okay, so you would take those two equations, put them into matrix vector form. The determinant of this matrix would have to be 0. So here is that determinant. You set it equal to 0 and you solve. Now notice that Maple comes back with lambda is the negative of an integer squared, because that's what down the score z3 means, or lambda equals 0. And you have to check out these two cases separately. So here I'm letting lambda be a minus n squared because it just looks better. This is what the solution looks like. Begin simplifying just as we did before, assuming that n is a positive number. You get this. Maple doesn't know that it's real or an integer. Well, it knows it's real because we said positive, but it doesn't know that it's an integer. So a plus bi form, each of these imaginary exponentials gives you a sine and a cosine. You want to collect those. This is the general solution, but we have to apply the boundary conditions to the derivative. It's x prime of 0 and x prime of pi. So we're going to be working with this expression. So apply x equals 0 to this expression. You get this. Then apply x equals pi and this condition. You get this equation. If you assume now that n is an integer, you have this. If you look at what this is saying, the difference between C1 and C2 has to be 0. So you go back to this solution, not the derivative, the solution. This difference is 0. That knocks out the sine term, leaving you with a multiple of the cosine term. And that's how we have concluded here that the eigenfunctions are multiples of the cosine. And again, if we were using commands and we use the dsolve command, we could apply this assuming option, assuming n is a positive integer, and you would immediately get that x is cosine. Well, I wanted to see how robust my approach to the Sturm-Liouville computation was. So I began with separated boundary conditions. Okay, so a little bit more complicated boundary conditions. Then I said, I'm going to make this even worse. I'm going to take an equation that's not formally self-adjoint. This y prime term makes it not formally self-adjoint. Would the same approach work? Okay, I would plug in the exponential guess e to the mx to this differential equation. I'm going to get the characteristic equation, which I would solve for the characteristic roots. Now, from the characteristic roots here, I observe that if lambda equals 1, I get a repeated root. So that's the special case. Lambda equals 1. It's the double root, and the solution is different for that case. One solution in the fundamental set would be e to the minus 1x. But because it's a repeated root, the other solution in the fundamental set would be x times that. So I factored, and I'm going to have a plus bx times e to the minus x. And I've got to check to see if lambda equals 1 is an eigenvalue, but I have to use this solution to check that. Okay, so I've unassigned S. I want to make S be this solution. Make it a function so that I can apply the two boundary conditions. And again, I take the equations that I get and I put them into matrix vector form, get the matrix, get its determinant. If you look at its determinant, you can see the determinant here can never be 0. So lambda equals 1 will not be an eigenvalue. So we now take the general case. Again, unassign S so that we can right, S of x, this is now the general solution in those cases where lambda is not -1. You have e to this root and e to this root with an x there and an x there, and a and a b are the two arbitrary constants. So I'm going to do the same thing that I did before, and maybe this will look better if I make the font a little bit smaller. Here are the two equations. I put them in matrix vector form, grab the matrix, get its determinant, but now the determinant is pretty messy. So I hit it with a simplify, then I hit it with a collect, and I looked at this equation and I said, there's no way to solve this analytically, so I have to solve it numerically. So I told Maple, give me the list of roots starting at 0 until you run out of space to write them. So here are the first 1, 2, 3, 4, 5, 6 values of lambda. Those are the eigenvalues, but they had to be computed numerically. But the process that I went through to get them is the same process. Apply the boundary conditions, get a matrix, get its determinant, because the boundary conditions are homogeneous. And we also notice that lambda less than 1 stuff is real. But when lambda is greater than 1, we have imaginary exponentials to deal with. So the equations that I'm looking at now are kind of messy. I tried to come up with a way to make things a little bit more compact. So I said, okay, let me take the first boundary condition and apply it. There's an a and a b. I isolated the a, and I took that and put it into the expression, the general solution. Looks like this. Now I said b is a multiplier. B here, b here. B is a multiplier. Okay, because the eigenfunctions are determined up to an arbitrary multiple. Okay. Why don't I just set that b equal to 1, is what I did. So now I have this expression for the eigenfunctions. Now, got to be careful here. When lambda is less than 1 and when lambda is greater than 1. When lambda is greater than 1, I've got imaginaries to deal with. So let's take the real part, and because there's an x and a lambda both, you need an eval c to make Maple do the calculation, and we'll do a simplify, but we have to assume that lambda is greater than 1, making this stuff complex, so we get this expression. Alright, so here is an expression. It's got sines and cosines. Lambda greater than 1. This is what an eigenfunction is going to look like. Can we do better? Well, why don't we normalize this by dividing by its value at x equals 0. You know what I mean? You're determining the solution up to an arbitrary multiplier. So this is a normalization. Well, this is a little bit smaller than this, a little bit shorter. And remember, either the first eigenvalue, lambda, is less than 1. So let's take this expression and evaluate it for that first eigenvalue that we computed numerically. You get this eigenfunction. Then for the rest of the eigenvalues, which are all greater than 1 now, we'll use this expression, because this expression is valid for lambda greater than 1. And I used it to write 5 more eigenfunctions. Then I graphed those eigenfunctions, and they behave in a manner which I think is reasonable for such a problem. Now finally, I'm going to take a look at a numeric technique that the dsolve command supports for Sturm-Liouville problems. Let's take our differential equation. It's not even formally self-adjoint. Here is the first boundary condition. Here is the second boundary condition. Make a system in which I have the differential equation, the 2 boundary conditions, and a third condition which I just make up. And that's because lambda is unknown. And this is a numeric calculation. So something has to be done about giving one more condition for Maple to deal with the unknown lambda. Okay, you apply dsolve to this system, and you tell Maple this is a numeric calculation. So Q1 is really a collection of procedures. If I evaluate lambda at Q1 of 0, I will get the first eigenvalue. Now that's a little bit puzzling if you don't see what Q1 looks like. Q1, list of these functions in here, evaluate it wherever you like, 0.1 x equals something, which you gave it, y corresponding to that x, derivative, and lambda. No, lambda is going to be a constant no matter what you put in here. Lambda is going to be a constant. So I'm taking this list and I'm evaluating this list or using this the information in this list to evaluate lambda, so it picks out this number, and so that's the first eigenvalue. Now you can continue trying to get the next eigenvalue. See, now Maple needs a lot of help. You've got to give it an approximate solution for the eigenfunction. So you need to know what the eigenfunction looks like. So very much like the Rayleigh-Ritz technique, which I'm going to be looking at in a future webinar, you almost need to know what the eigenfunctions are before you calculate what they are. So you're going to have lambda somewhere near 1, and you do the same kind of a stunt, and you get the second eigenvalue. You want to get the third one, you've got to give Maple a very good hint about what that third eigenfunction looks like, and you compute an eigenvalue near lambda equals 4, and you get the next eigenvalue. And if I graph those 3 that I've just computed numerically, I see that they behave the way they're supposed to behave.